Welcome everyone to our meeting. Well, our speaker today is Mario Velásquez from the Universidad Nacional de Bogotá. And he is going to talk about obstructions to positive scalar curvature on manifolds with crystallographic fundamental group. Please, Mario.
Okay, thanks to Gisela and Guillermo for the invitation. And today I will talk about some results that we have about obstruction of positive scalar curvature, some positive results and negative results over this class of groups. This is a joint work with Noé Bárcenas at the Universidad Nacional Autónoma de México. Okay, let me give you a brief outline of the talk. I will start recording what is scalar curvature, the Dirac operator, and the famous Lisner-Ovid formula. Then a Stolz theorem and the Gromov-Lawson-Rosenberg conjecture. I will talk about briefly how to prove this conjecture, and then talk about certain crystallographic groups, and finally I will talk about the counterexample. Okay. Scalar curvature. The scalar curvature is the most basic notion of curvature. It's a generalization of the Gaussian curvature. Consider M via a Riemannian manifold. The scalar curvature is a smooth map defined from the manifold to the real numbers, whose value at a point S of x appears in the Taylor series expansion of this Gaussian map, where the numerator is the Riemannian volume of the geodesic ball of radius r around the point x, and the denominator is the volume of the usual ball of the same radius in Rn. It is this term in the coefficient of the R square. That is the scalar curvature. Is the generalization of the Gaussian curvature defined on surfaces. Okay, what is the Dirac operator? Then let me recall a definition. A spin structure on a manifold of n dimension is a principal spin n bundle, but what that we call spin of M over the manifold M, and away with a double covering map Q from spin of M to the SOM, that is the bundle of frames, of orthogonal frames, over M, which is a spin N equivariant, where the action of a spin of the spin group on the bundle SO of M is given by the natural projection, and which makes the following diagram commutative. Then we have this commutative diagram. We have this commutative diagram. That, in other words, we could say that we have a lifting of the structural group from the orthogonal group to the spin group. Okay, that is the spin structure. Now consider the Clifford algebra. The Clifford algebra is defined, for example, as the real set2 graded real algebra with n generators, E1 to En, satisfying the Clifford relation. That's the relation that appears here. And we can define the spin group as the group of even products of unitary elements in Rn. That is can be defined inside the Clifford algebra. Then we have a natural conjugacy action of the spin group on the Clifford algebra. Using this action, we can define the spinor bundle. How to define it? We start with the spin structure with the bundle spin of M, and we can change the fiber. We can associate a vector bundle S over M with fiber the Clifford algebra. This bundle is called the spinor bundle, and over the spinor bundle we can define the Dirac operator. What is the Dirac operator? The Dirac operator is a self-adjoint first-order elliptic differential operator, D, acting on the space of smooth sections of S, what we denote this by gamma of S, and one important property of the Dirac operator is the Lisner-Robles formula, this formula that says that the square of the Dirac operator is related with the scalar curvature. The square is equal to the connection composed with the adjoint of the connection plus 1/4 scalar curvature. Why this is important for us? Because using this formula, we can relate, or we can do the following computation, relating the kernel of the Dirac operator with the scalar curvature. We have that as the E self-adjoint, we have the following inequality for phi, smooth section.
I have a question.
Yes.
This space of smooth section does this come with some topological structure? So for me, a Dirac operator acts on some Hilbert space associated to like L2 of like the manifold.
Yes.
Like what sort of a vector space is this gamma S?
Yeah, inside the, for example, you can consider inside of the space of L2 sections, for example.
Okay, I see.
With the L2.
So it's larger than L2 of the manifold.
Yes.
Okay. Thanks.
Yes. Okay. Yes. Okay. Then we can do this computation. Then the norm of the D of C is equal to this inner product, and then you, as D self-adjoint, you could move D from the right side to the left side, use the Lisner-Robles formula here, and then you use the distributive property, and we get this inequality. Okay? We have this inequality. This inequality says that the norm of D of C is greater or equal that the scalar curvatures times the norm of phi to the square. New norm of phi square. It means that if the scalar curvature is strictly positive, then the kernel of D is trivial. We can deduce from this formula this fact. And then let me say one thing more. As the Clifford algebra is set to graded, we had a decomposition of the space of sections. We have even sections and odd sections. Even section and odd sections. And the Dirac operator takes this form, has this matrix, and we have that as D is an elliptic operator and self-adjoint. We have that we can compute the index of this D plus, the index of D plus, as defined as the dimension of the kernel of D plus minus the kernel of the, really minus the dimension of co-kernel, but the co-kernel of D plus is equal to the kernel of D minus, and this expression is defined or is equal to the superdimension of the kernel of D. But we already know that if M admits a metric of scalar curvature, this superdimension is 0. Then the existence of a metric with positive scalar curvature implies that the index of D plus is 0. Then the existence of a metric with positive scalar curvature is related with the index of an operator, of an elliptic operator, D plus. Why this is important? Because we could compute the index of D plus in terms of topological information of the manifold. Okay, and the question is if the converse is true.
Michael,
why? Because yes,
there is some echo. Maybe you are connected to the audio with both your computer and your iPad.
Okay. Let me check. No, I don't know why this is happening. No.
Desconectar el audio a la computadora, del Zoom de la computadora.
Pero en el iPad no estoy conectado con audio. Déjame ver.
Desconectar el audio a lo que no estés compartiendo el micrófono.
¿Se sigue escuchando eco?
Sí. Ahí. A ver ahora. Ahora
Ahí.
no te... A ver.
Ahí se escucha. ¿Se escucha eco ahí?
Sí.
Oh my God.
No, vos te estás compartiendo con la tablet.
Sí.
Entonces, en el Zoom de la tablet pone desconectar audio.
Ok. Ahora.
Ahí está, ya está.
Listo, gracias.
O no sé. Bueno, no importa. Digamos así.
Okay. Let me continue and then we... Okay. So we have then that the existence of a metric with this positive scalar curvature implies that this index is 0, and this index can be computed using just topological information. The question now is, if we know that the index of D plus is 0, if we can conclude that there exists a metric over M with positive scalar curvature. Okay? We have this very, very famous theorem of Atiyah-Singer that tells us that the index of D plus can be computed only using topological information of the manifold M. And it is interesting because, in particular, it does not depend on the Riemann metric used to define D plus, using to define the operator D and the operator D plus. The index can be computed only using topological information, the manifold, as an integral of certain characteristic classes. But we have the other question. The other question is if the converse is true. It means that if the index of the plus is 0, there exists a metric with positive scalar curvature on M. We have this theorem, but it is not true in general, but we have this theorem. It is a theorem of Stolz that says that if M is simply connected, spin manifold of dimension 4K, then if the index of the Dirac operator is 0, then M admits a positive scalar curvature, a metric with positive scalar curvature. Two questions appears here. The first one is why manifolds of dimension 4K? Why we have this obstruction of dimension? And the second one is why M has to be simply connected. The answer of both questions are related with K-homology group, because the index, we can generalize the definition of the index of D plus, taking values in a K-homology group. Okay, so let me recall the definition of K-homology groups, the real K-homology groups. These definitions was given by Atiyah, Bott, and Shapiro. It says that we can consider the Grothendieck group of isomorphism classes of finally generated Z2 graded Clifford modules. This Grothendieck group is denoted with this Gothic M. This Gothic M. And the K-homology group, the orthogonal K-homology group, is defined by this quotient. The quotient of the Grothendieck group over the Clifford algebra of dimension n module, the modules that can be extended to n plus 1. This is that pullback. Okay? It is called the nth orthogonal K-homology group of the point. And we can compute explicitly that groups are aperiodic, that we get integer numbers for n equal to 4k, and Z2 for 8k plus 1 and 8k plus 2. That is the reason, because the above theorem is only true for n equal to 4k. The reason is because the index in that case takes value in integer numbers, but in the other cases could be 0 or could take values in Z2, in C2. But let me generalize the definition of the index. Then, in general, we have that the kernel of the Dirac operator and sorry, here is D plus. The kernel of D plus and co-kernel of D plus are naturally modules over or harness CL of n modules Z2 graded of finite rank. Then we could define the Clifford index of the Dirac operator for manifolds of any dimension as just the difference of the isomorphism classes of the kernel and the co-kernel. This difference lives in this orthogonal K-homology group, KON of the point. This number, or this value, is called the A hat genus of M. The A hat genus of M. And we have now this theorem of Stolz that says that if we consider this generalized version of the index, we have that if M is simply connected, a closed spin manifold of any dimension greater than 4, then M admits a metric of positive scalar curvature if and only if the A hat genus of M is equal to 0. Okay. What is the idea of the proof? The idea of the proof is the following. Let omega n spin be the group of Bordism classes of spin manifolds of dimension n with this union as the operation. And we are saying here that two spin manifolds are equivalent. Let me give us a quick picture. For example, we have here M, we have N. We are saying that two spin manifolds are equivalent if there is a spin manifolds of a dimension n plus 1. W, for example, such that the boundary of W is equal to M union with N, but with the opposite structure. That is the spin group, and the operation is the union. Okay. This group is the Bordism group, the spin Bordism group, and Stolz proves the following property: the hat genus and the existence of a metric of positive scalar curvature depend only on the Bordism class of M. What means that? It means that if M has positive scalar curvature and is Bordan to N, N also has positive scalar curvature. And if we can compute the 8 hat genus of M, and we have another manifold that is Bordan to M, then the 8 hat genus is the same for the Bordan for the manifold Bordan to a manifold Bordan to M. Then we have a well-defined map from the spin group of n dimension to the orthogonal K homology group of a point. Just saying that this map is just defined as computing the A hat genus of n. It is well defined because we have this property of Stolz, proved by Stolz. And what is the advantage of doing that? Because we can compute explicitly generators of this spin group. Explicit generators localizing into and inverting into, but using that explicit generators, we could show that any manifold such that the A hat genus is 0, we can construct a positive scalar curvature over the manifold. How to do that? Take explicit generators, construct a explicit generator of the spin groups, and showing by hand that each one admits a metric of positive scalar curvature. That is the idea of the proof. And it is important to consider the spin group because we can do or we can show the existence of metric of positive scalar curvature just for the generator, not for every spin manifold. That is the idea of the proof. Okay. A question so far? No? Okay. Now, I will talk about the case of manifolds that could be non-trivial fundamental group. To do that, we need to talk about classifying space. Okay, let me give a definition. Let P be a group, then a model for the classifying space. EP is a PCW complex that have trivial isotropic groups that are free, and that is weakly contractible. That is a model of EP. We have this theorem. The quotient map from EP to the orbit space, BP, is the universal P principal bond. BP is unique up to homotopy equivalence. Just let me give a couple of examples. For example, for the integer numbers, EC is the real numbers with the translation action, and BC is the circle. A second example, the classifying space of cyclic group set C over M is the colimit of odd dimension spheres with the action given by multiplication of roots of the unity. We need to take this colimit because the spheres are not weakly contractible, but if we take the colimit, we get a weakly contractible space. Okay. Now, how manage the case of non-simply connected manifold? The idea is just take the universal covering and work in the universal covering. Then consider a manifold M, a spin manifold with fundamental group P. Then we have the universal covering denoted by M hat or M tilde, sorry. Then M tilde is a simply connected spin manifold, and the quotient map from M tilde to M is a P principal bond. We already know that the map from EP to BP is the universal principal bond, P principal bond. Then we can there exists a unique map to homotopy M to BP, such that the pullback of EP under this map is homeomorphic to M tilde. This map U is called a classifying map of the classifying map because it is unique to up to homotopy. This map U is called the classifying map of M. The classifying map. Suppose, for example, that P is a finite group. Then we have M tilde, and we have the Dirac operator D tilde over M tilde. This operator commutes with the action of the Clifford algebra and also commutes with the action of P. Then we have an action of the algebra, the Clifford algebra tensor with the real group algebra, RP. And doing similar things as before, we can define the Clifford P equivariant index, just saying that the kernel of the tilde is a module over this tensor product, Clifford algebra tensor, the real group ring. Also, this happened with the tilde. And this difference between the isomorphism classes lives in a K-homology group. In this case, it is the K-homology group of the real group ring. And this number is called, or could be called the equivariant 8-hat genus. This is the P equivariant 8-hat genus. In the case that the group is finite. If the group is infinite, it is also possible to define this equivariant Clifford index, but we need to change R of P for a completion of it. In this case, it will be the reduced C-star algebra of P, denoted by CRP of R. The analytic details of that are more complicated, but it is possible to do. And we have this theorem of Rosenberg that if M is a spin manifold, we can, with dimension greater than 4, if this manifold has a metric with positive scalar curvature, then the 8-hat genus, defined this equivariant 8-hat genus, is 0. Is an analog, or it is proved using an analog of the Lisner-Lewis formula at the beginning, but we need to work over the the universal covariance. Okay, and what is the conjecture? The conjecture is analog to the theorem of Stolz. It says that if we have a spin manifold of of dimension greater than 4, and this equivariant 8-hat genus is 0, then M admits a metric with positive scalar curvature. That is the conjecture. It says that we only need to compute this equivalent 8-hat genus in order to know that if a spin manifold admits or not a metric of positive scalar curvature. How to prove this conjecture? We can try to follow the same strategy as Stolz. Then we need to define a convenient Bordism group. It is the spin group, but over the classifying space. How we define it? We need to consider not Bordism of manifolds. Instead of that, we need to consider Bordism over maps from manifolds to the classifying space. Then we need to consider Bordism classes of maps from M to the classifying space, and inside this group, we define the Bordism classes of manifolds, of maps, sorry, from manifold to BP, where the manifold admits positive scalar curvature. And the Gromov-Rosenberg conjecture can be translated in terms of the Bordism groups, just telling that if M or if the Bordism class of M of the classifying the M with its classifying map belongs to the kernel of the A hat genus, then we need to find or to define a metric of positive scalar curvature. That is the idea. Taking explicit generator of the kernel of the A hat genus over as a subset of the spin group, of the Bordism spin group. And for every generator, try to define a metric of positive scalar curvature. That is the idea. But unfortunately, this idea will not work. Why? This not work because sorry, here we have a mistake, but why this procedure will not work? Because this group, even for simple P, is very difficult to compute. At most impossible to compute. Very difficult to compute. It is not as the case of simply connected manifold. In the case of simply connected manifold, we Stolz compute these groups. These spin groups over the point, can be computed explicitly. Generators inverting 2 and localizing at 2. But for the classifying space BP, it could be very difficult. Then this strategy will not work. How to manage this difficulty? We need to define a substitute for spin Bordism groups. We need to define a substitute for spin Bordism groups. And for this, let me recall the definition of geometric homology. Okay? It is just an informal definition of geometric homology. So let X be a space and positive integers and non-negative integer. The nth geometric orthogonal K-homology group, denoted by KO n of X, is defined as the quotient of the set of triples M, E, F, where the first one is an n-dimensional spin manifold, the second one is a smooth real vector bundle, and F is a continuous map. Then we have something like this. We have a map over X and a vector bundle, a real vector bundle. Something like that. And over the set of these triples, over the class of these triples, we define a equivalence relation generated by Bordism in a similar ways as these Bordism groups, but also using the Thom isomorphism and with the operation of disjunction. For negative degrees, just define k of n of x just as ko of minus n x. Okay, that is the geometric homology groups. These groups will be isomorphic to the Kasparov K-homology groups, but the proof is not trivial. There is a couple of papers of Schick and others proving that. But okay, we have this geometric K-homology group, and the index morphism can be generalized to a map from the geometric K-homology group of the classifying space to the K-theory group of this real algebra, R of P, just taking the index. Okay, this map is called the assembly map. Just taking, if we have a triple MEF, we can take an index of the Dirac operator, of the twisted Dirac operator, of defined over this bundle S tensor E. Because we have the spinor bundle S, and we could tensor with E and extend the Dirac operator to this to section of this bundle. This map is called the assembly map, and we have the following. We can define another K-homology group. It is called the connective orthogonal K-homology groups. Defined or not defined, determined by the following properties. We have these groups KO, small KON. It satisfies the properties to become a extraordinary homology theory. It means excision, homotopy invariance, major arbitrary sequence. And for negative degrees, we have that these groups are zero. And also, we have a natural transformation in X. It is the periodicity map. It's called the periodicity map. The periodicity map. From the connective K-homology group to the periodic K-homology group, the orthogonal K-homology group, in such way that if X is a point, in positive or non-negative indices, it is an isomorphism. Another way to say the third property is to say that the functors Ko, small Ko, n are universal among those satisfying properties 1 and 2. There exists formally we can prove that these groups, these connective groups exist. You could, for example, take the spectra of K-theory and take the connected cover of the spectra, and the homology theory obtained in that way is the connective K-homology groups, for example. Why these K-homology groups appears here? Because we have the following. We have that these spin Bordism groups are extraordinary homology theories, and satisfies properties 1 and 2. Just by the A-hat genus. The A-hat genus define a map from the spin group to the orthogonal K homology groups. And these spin groups, sorry, here is spin group of X. These spin groups has the property, satisfies the properties 1 and 2. Then the 8 hat genus factorize through K homology, connected K homology groups. Then we have a natural transformation F, satisfying that the 8 hat genus can be written as this composite. A composed with P, composed with certain natural transformation F. So we have this theorem of Jung and Stolz that tell us that if we consider these connected K homology groups, these positive K homology groups, KON plus of BP, whose elements are the image of classes, or Bordism classes of metric with positive scalar curvature with classifying maps. This group captures all the information relevant to the Gromov-Rosenberg conjecture. In other words, if we want to prove the Gromov-Rosenberg conjecture, we can prove that these positive K homology groups are the same as the kernel of A composed with P. This A is the assembly map, and this P is the periodicity map. Then we could try to use the same strategy as Stolz at the beginning, but instead of use the spin groups, we can use the connective K homology groups. What is the advantage? The advantage is that these K homology groups are more accessible to make computation. You can, for example, use the Adams spectral sequence to try to compute these K homology groups for every group P. Try to compute these K homology groups and try to find explicit generators and try to define by hand a metric of positive scalar curvature for each generator. That is the strategy that works in some cases. Okay. We do not lose information if we substitute speed Bordism by connective orthogonal K homology groups. Okay, let me, I don't know, how much time do I have?
10 minutes, maybe 8, so we have 2 minutes for questions.
Okay. Let me, sorry. Let me, I am out of time. Okay, let me give some big ideas about our results. Now, we consider integer matrix, invertible row, invertible matrix of order M. Then row induce a graph structure on this Cartesian product, just saying that this variable t acts on M via the matrix. This group is denoted by this Snyder product. This group has a natural action of R to the n just by, again, let act T be a diametric row. And the question is, what kind of, or the question is, if that group, those groups satisfies or not the Gromov-Lawson-Rosenberg conjecture. These groups contains some of the planar groups. For example, if we take this matrix rho, we recover this planar group, P3. If we take this matrix, we recover this planar group denoted by P6, and so on. These classes of groups contains some planar groups and some other crystallographic groups. Our theorem is that if we consider these crystallographic groups with M odd, and such that the matrix rho has the following property, the property of that the eigenvalues are primitive and roots of the unity, then the group satisfies the Gromov-Lawson-Rosenberg conjecture. That is our result, our first result. And the idea of the proof, just let me say that the idea is to use algebraic properties that are derived from the property of the eigenvalues that allows to reduce the proof of the Gromov-Lawson-Rosenberg conjecture to the case of cyclic groups. But we already know by a result of Botvinnik that the Gromov-Lawson-Rosenberg conjecture is true for that class of groups. Then we are done. That is the positive result. And over this class of groups, we also have a negative result. We have this counterexample, a very famous counterexample of Thomas Schick, that says that there is an spin manifold of dimension 5, such that the fundamental group is isomorphic to Z4 times Z/3, such that this equivariant A hat genus is 0, but the manifold does not admit a metric of positive scalar curvature. We can adapt the strategy of Thomas Schick to our case. Well, I don't have time to explain the proof, but the idea is that if we consider, again, an integer of a positive integer square free, and let rho be an integer matrix of order m, if the non-free part of the module set to the n, recall that using rho we have an action of z over m. We have an action on z to the n. If we consider this action as the rank of the fixed points are at least 4, then this group, this semi-direct product, is a counterexample of the Gromov-Lawson-Rosenberg conjecture. Recall that, for example, if rho does not have sorry, if the eigenvalues of rho are primitive roots, n primitive groups. Then the group satisfies Gromov-Lawson-Rosenberg. On the opposite, on the other hand, if the matrix has the fixed points has rank at least 4, then the group is a counterexample for the Gromov-Lawson-Rosenberg. Then inside the same class of groups, we have positive results for the Gromov-Lawson-Rosenberg conjecture, but also counterexamples for the Gromov-Lawson-Rosenberg conjecture. And that's it. Thanks for the invitation.
Thank you very much, Mario. Nice talk. Any
Thank you.
questions for Mario? Let's see. Okay, Mario, so you mentioned that for cyclic groups, finite cyclic groups was the conjecture true.
Yes.
Now you have these results, and there are other examples for the conjecture to be true.
Yes.
Yes, many.
Yes, we. Sorry, again.
Also, cyclic groups, these groups that you mentioned, and what other groups, for example?
Okay. Yeah, for example, we have this result of Botvinnik that proves that really the result proves that that finite groups with periodic cohomology satisfy the conjecture, for example.
Okay.
There are another examples, for example, groups of this kind, SL2 of set 1 over P, for example. The square matrix, the linear group of size 2 over these rings set over 1 over P. It is also true, the Gromov-Lawson-Rosenberg conjecture. But I have to say that in comparison, for example, with the Baum-Kohn conjecture, we don't have counterexample for the Baum-Kohn conjecture, and the community, I mean, believe that the Baum-Kohn conjecture is true for all groups. Instead of that, in Gromov-Lawson-Rosenberg conjecture, we had a lot of counterexamples.
Okay.
The first one, yeah, counterexample. The first one was defined by Schick, but also there is a huge family of counterexamples. In particular, our groups, our results console and infinitely many counterexamples.
Yes, the Baum-Kohns with trivial coefficients, with complex numbers.
Yeah, with trivial coefficients. Yes. Yeah. With trivial coefficients.
Okay. Okay, if there are no more questions, I will stop the recording.